Alrighty. I think we're ready to get started. Just want to say thanks to everybody for joining us on the last session of the day. My name is Eric Hochmuth, and this is my colleague Robert Grayler. We work for Monsanto, and Monsanto's research and development IT organization, supporting all of the researchers in Monsanto. However, the actual use case that we're going to talk about is our first data product that we've actually released and developed for our growers, the farmers that we develop products for. And kind of really the motivation behind this talk is when we started dealing with spatial data, there really wasn't a lot published about doing spatial analysis in Hadoop and HBase. I think most of the content that was freely available was dealt with dealing with point-based data, extracting a lat long from a log file or a tweet. And we're dealing with a lot more complex polygons and shapes, so we wanted to kind of share our experiences of doing spatial analysis on Hadoop. So a little bit about Monsanto real quick. We're the world's largest company focused 100% on agriculture. Our mission is to provide more fuel, food, and fiber, all while using less, so using less inputs, less water, less irrigation, same amount of land. If you think about the world population of 7 billion people, and an additional 2 billion to 9 billion by 2050, it's going to be quite a bit of mouths to feed, all while retaining the same amount of land. So we're committed to doubling yields again while using the same amount or less by 2030. So exactly how are we going to do that? Through data and analytics. So if you think about the modern day farm, it's a highly instrumented and automated environment. Many of the equipment, the tractors, the planters, are precision guided, highly automated devices. And in many cases, the grower doesn't actually even drive the tractor. It's completely automated and will automatically go up and down the rows by itself. And many of these devices, these tractors, planters have 20 plus sensors embedded on them, collecting all kinds of information like solar radiation, the elevation, the moisture, the elevation, the yield, literally counting every single seed that it plants in the ground. And so our goal is to leverage as much of that information as we can to help the grower, the farmer, maximize his yield potential on every single square foot of land. If you think about it, the grower really only has about 40 opportunities in his life to provide the best product for his family as well as for us. All right. So our entry into this market of using all this data information is really through this platform that we're developing called Integrated Farming Systems. And you can really think of this as a giant recommendation engine for the grower. Just like you'd get a recommendation from Amazon, for what books to buy, Netflix, what movies to rent. Our goal is to take all that data and information and build a recommendation system where we can provide the growers with data-driven decisions. And like I said, this is a platform, but by 2014, our first entry into this platform is going to be the field scripts. We're going through a beta release now in Iowa with a select set of growers. And this field script product is going to take key information about the environment and will provide the grower with a recommendation based on his environment, based on his field, looking at key attributes, what specific hybrid or product to purchase to optimize his yield potential, as well as for every square foot of land, how many seeds to plant in that square foot of land. Because if you think about a field, it's not uniform. So the different soil types, the different elevation, all impacts the amount of seeds that you can actually plant, and then obviously impacts the yield potential. And just kind of some proof is in the pudding. We're running some trials, I guess, a year ago, and you can kind of see from our results using data to select the hybrid and select the appropriate planting density. We're seeing, on average, 5 to 10 bushel acre advantage. So if you think about a farmer who's got 600 acres, getting additional 10 acres, best case scenario, per acre at $6 an acre or bushel, that's a pretty significant impact to his bottom line. All right, so a little bit, and then being a full product or a full platform, we kind of envision a world where the farm is kind of viewed as a system where for all that information we can recommend to the grower what product to buy, how to plant it, precisely exactly when to plant it based on weather conditions, what product and when to apply some type of field treatment during the year, and then precisely when to harvest, all to maximize his yield potential. So just a little bit about the use case. Like I mentioned before, we're leveraging all that environmental data. So we're really looking at building a spatial ingestion pipeline that can bring in all sorts of dynamic data sets, publicly available data that you might get from the government, or proprietary data sets that we might have purchased through some of our partners, as well as combining that with our own internal genetic information, as well as taking data that the grower provides, his historical yield data, bringing that into a common platform where we're performing QC on it. We're converting it to a canonical format so that we can easily link it together and look at every square foot of land and look at all the environmental attributes of each one of those square feet of land. Then feeding it into an analytics platform where we're leveraging R and Revolution Analytics on Hadoop that then spits out a field script. And then kind of what's not shown here is we take that field script, deliver it to an iPad that's running the tractor, that then will instruct the tractor exactly how many seeds to plant in each square foot of land. So some of the challenges or the opportunities that we had is we're not dealing with your typical tabular or textual data. We've got really rich dynamic data types like vector-based shapefiles, which aren't necessarily easily splittable. We've got binary data types like raster satellite images, and we need to take all these different data types that might be in different spatial projections and convert them to a common format, but then still have tabular metadata associated with all of that spatial data that we then have to link together. And then a lot of the computations that we're wanting to do are very dense and very complex. So we're being point-based, not looking at just a large area, but having to look at a square foot and determine something like slope or flow control, where we actually have to look at the neighbors, look at so many neighbors out from each square foot. We do that for 1 square foot, then we have to do it for the next square foot. So very complex computations on extremely dense data. So I think this would be a good story if I could then say we put this in Hadoop, we got the performance that we wanted. Unfortunately, we didn't do that. Our initial thought was to put this on a relational database that had spatial functionality built in to it. Our ideas were that the spatial functionality, the support for the complex spatial data type that the database already had would accelerate our ability to get the product out the door. Unfortunately, that didn't quite work. We actually found that for the density of the data and the complexity of the computations, the commercial database engine actually didn't meet some of the SLA and some of the needs that we had. And so the vendor actually patched their database engine for us, adding additional spatial functionality and performance enhancements. I don't know if it's fortunately or unfortunately, it still didn't meet our needs. So you can kind of see from the times, just trying to deal with 8% of the data, just the corn states, just to process that data was taking, on the magnitude of longer than a month. And some of the feedback we'd get was, some of that is reference data that we're generating, and you're only going to generate it once. But I don't know how many of you guys have developed a system where you've never had a bug, so the chance of having to do that actually once was fairly unlikely. And then just having to go through all the trade-offs that you're used to when dealing with relational databases, storing the data compressed and uncompressed, which then impacts your performance, your read-write performance. And then we were actually pushing the compute down into the data using PL SQL. That's not exactly the easiest thing to test. And then a lot of the recommendations we'd get would, buy a bigger database. And unfortunately, with the platform we were using, that's not exactly cheap. So we've been using Hadoop since about 2009 for a lot of our genomic analysis. So we thought at a minimum we could look at leveraging MapReduce for some of the embarrassingly parallel processing of the of the raster or the vector files that we're dealing with. So we had an existing CDH cluster that we plan to leverage, but then also having to provide real-time access to the data for both the recommendation engine as well as a lot of the existing spatial tools that our research community is using, like the ARC desktop. So we then proceeded to build a customized data model for storing all of that data in HBase, which Robert's going to talk about here in a second, as well as building a data service layer that implemented a lot of the spatial functionality that we needed. So I'm going to turn it over to Robert.
All right, thank you. So now for the fun part here for you. So if you heard Eric talking about the different file formats, one of the first problems we had is with the elevation and soil data sets. One of them was in raster format, one of them was in vector. Now, vector format gives you huge advantages, a lot of data, nicely defined data in that, but it is not easy to process. So we first had to come up with what standard are we going to use? Are we going to use the vector or are we going to use the raster data? Initial comparisons, the raster format was, on the magnitudes of 10 plus times faster than the vector. So what we did was using Hadoop streaming, we would take the vector data, transform it using GDAL into raster format, and upload all this up into HBase. I mean, not HBase, wow, HDFS. So what that did was that allowed us to create a single standard format for ingesting this geospatial data. So some of the problems we ran into was just, getting the GDAL installed and everything, making sure we had the right packages for it. Some of the shape files were actually so large that we couldn't turn them into a single raster. We had to split them apart, make them into multiple rasters, and for those of you that are familiar with shape files, they aren't squares either. I mean, they are complex shapes upon themselves. So it took a little bit of time just to get the data into a format that we can even begin processing it. So once we actually had the raster data in HDFS, that's when the real fun started. Raster files are basically JPEG files. They're image files that have metadata associated to them. So what we ended up having to do was create generic input formats and record readers that would split this data out in a format that we could easily process it. As part of that, we determined that the best location for the attributed data was going to be in the HBase. Initial loading of creating billions of records in HBase through the put framework of MapReduce turned out to be incredibly slow and just crashed our clusters. So we decided to go with the bulk H-file input format. What this allowed us to do was directly write the H-files and then have HBase just take them and run with them. This also made it easy for us to move environments. So I could generate these huge HBase tables in the lower environments, move the H-files from one cluster to the next, and just hook them straight up into HBase. No need to do any real regression testing, just basic smoke testing, and you're good to go. One of the big challenges we had with this is the raster data have metadata associated to them. The image files are in binary format by row, and the rows are no guaranteed order inside of the file itself. So we had a lot of problems with object creation and split sizes and read sizes. So it took us a little while to kind of work out that magical equation going between balance of speed and memory on what part of the MapReduce framework took each one. Once we actually got it into the mapper, the next challenge came is that we actually are creating 6 times as much data as we were importing in the case of the elevation data set. Elevation data set gave you elevation. We calculate additional attributes beyond that and store those in the HBase. So we were having massive I/O spills and buffer flows. So we had to spend a good amount of time adjusting the configuration parameters for I/O sort, file read buffer, record buffer, and making sure that we could really get those disk spills down. So Now we know how to get these things in the HBase. The real challenge comes is, just here, what are we going to use for this HBase key? So one of the standard geospatial formats is Geohash. And basically, this is a byte key that tells you whether or not you're north or south, east or west of your current location. And based on the length of the key, you can get to a small area of land. This did not work nicely with us because of the data sparsity. We are currently only dealing with the US, and the fact that you'd have to have 2 different keys to query any one individual point. So we had to go back and really look at what could we do with this. So as you can see here, not only the only problem is that our farm is not a square. In the example you see there, you could have a river running through it, a house running in it. It's not a very nice geospatial shape. And on the bottom right of the slide here, you can actually see one of our UIs that not only is it just geospatial data, it's linked geospatial data. What you see there is actually the flow of water for a given area in the US. You need to know all of your neighboring grids to determine what way the water is going to flow. So we had this complex data and this complex structure that we had to store somewhere. So we basically took a look at the world and said, all right, how do you fit a grid onto a sphere? And lucky for us, it had already been built. It's the WGS84 coordinate reference system, most of you latitude, longitude. So what we did is we basically looked at the latitude and longitude of creating a grid system that we could map a spatial region directly to a certain area of the world. Once we overlaid this grid, we could adjust it to the finite size that we wanted, say be it a foot or a mile. We then ordered the grid, starting in the lower left corner, going west to east, south to north, labeled each grid cell. What this allowed us to do is now have a single ID that represents a geospatial point in the world. So we now can easily go back and forth between a latitude, longitude location in the grid. So, all right, now we know what our key is going to be for HBase. So let's just plug that cell ID in there. So our first table design was to create an HBase table that was keyed off of this cell ID. We had a single column family that contained all of the data in an Avro format. This became a real big problem. When dealing with the US, you're looking at 120 billion records. This meant that we had to do numerous scans or thousands of gets to get back the data. Because if you remember, the cells go west to east, south to north, so that a farm is going to cross those rows and have vastly different numbers. The other thing that we found out was that with the design of HBase, we had over 50% of our HBase table was just the metadata of those keys. So we had to take a step back and really think about this, and the way that we communicate with the application is what's referred to as well-known text, WKTs, the polygons. A polygon is going to consist of some acreage of a farm, a given farm being 150 acres, for test pilots and that. So we went back and went, all right, if we're always going to load a farm at one time or get all the data about a farm, why not start grouping these cells in a larger schema? That's when we came up with the concept of a supercell. What these supercells are is a collection of cells that we can store inside of HBase. For the purposes of what we built, we did 100 by 100 cells inside of a supercell. What this did, we then avroed all the attributes for that cell and created a way of referencing the cells within a supercell. When we put this into HBase, you're now looking at a maximum of 4 gets for any given farm of average size, up to possibly 10 gets. This was a huge performance increase. And since we were always needing to load the whole farm at a time, the extra memory to pull those rows directly out of there did not hurt us. The big thing here is that last note there, that the amount of data in our HBase tables dropped in half. The size of our HBase tables, excuse me. The exact same data was in both tables, but because of the overhead of having all of those column qualifiers, we cut it by a lot. What this also allowed us to do is move some of this code that does the geospatial queries, because we still are dealing with grids here. We don't know, again, a farm's not a square. So now we're kind of able to pull some of that into our logic, either inside of the MapReduce or inside of our Tomcat application that's set upon this, and do some parallel polygon queries and really return this data for your given farm incredibly fast. So some of the results here, we went from the 120 billion, rows down to about, 12 million. The load time versus the database solution, which had 4 states, took, 35 days. We were able to process the entire US in a matter of 12 hours. And it's all able to be returned by any of our applications in a matter of 1 to 5 seconds based on those gets for the farm. So we were able to really meet all of our SLAs, do it on hardware that was cheaper, and do it a lot faster than we could inside of the database schema. So that's all the slides we really had for you. I'm going to open up for questions now, but before I do that, I do want to thank Cloudera. We had a partnership with them for designing this, and they really helped us come up with some of these designs and help us proof it out. So open up for any questions anybody might have.
Can you give some examples of analytics that you can do once the data is in HBase, this high level?
Sure. So most of our analytics is at a field level, where we'll pull all of those different spatial layers for a particular field and then look at all the different spatial attributes. I unfortunately can't go into details as far as the specific analytics, since that's kind of our secret sauce that allows us to develop this product that provides that optimization for the grower.
Can you, maybe I missed it, but can you please talk more about the key the super key? What was in that Supercell? Maybe I missed it.
So
can you explain more?
what we did was we basically took the same concept of a cell, where what we did was we created another grid. So in the case of the cells, we had a grid where the cell was, let's say, a foot by a foot. You can take the exact same methodology and make what we're calling supercells, which are a mile by a mile. You can then, I'm using extremes here, you can then key that individual ID, once again going west from east, north to south, but at the supercell. You then can, using an algorithm that we have, you can then get your individual record from that collection inside of that supercell. So the supercell is still a straight ID that then is what we're keyed off of. It's all relative, yes.
And then based on the density of the data type, we can then, through metadata, pick what gridding system makes sense.
And one of the benefits of this is that, unlike Geohash, if you wanted to change your resolution of Geohash, your actual key would change because of the bits that you need. Having this gridded system, it's all just a number. We can actually change the size of our grid without making any code changes if we just change the underlying HBase table. Because when I said we're all talking in those well-known texts, when we send things back out to the applications, we send them back out a list of, here are the grid cells, the north, south, east, west corner. The ID is just for us to track. That's irrelevant for anybody outside of that. All they care about is, I got a square of this size. I don't know who stood up first. I'm sorry.
Oh, thank you. Building on this part right here, can you explain why you chose to do a arbitrary reference system versus an established reference cell system like MGRS or something to that effect? I've had to build similar solutions like this before, and we were asked to utilize the MGRS system as a key value for our spatial renderings versus an arbitrary system.
Yeah, I can't answer that. We actually weren't aware of any of those existing grid systems, and then some of it was based on the access pattern of the density of the data that we were looking for.
Can you tell us the size of your HBase cluster and the amount of data you have in HBase at this time?
So right now, our production HBase cluster is 20 nodes, and the size of our soil and elevation data sets is in compressed Avro format about 6 terabytes right now.
Do you get your metadata with each raster image that you get, or you have to generate it?
It is part of the raster format. When the raster is generated, there's header information, metadata inside of the raster. And that was one of the big complications, was that each raster is a different spot, and each of those rows are in different orders. So we'd have to move that along with the reader so we know which set of bytes to grab.
So in the Hadoop, you did that using MapReduce programming, or you did outside?
It's all done inside of MapReduce. So we had an import format that would kind of read those files, read the metadata, a custom record reader that would basically give the bytes to the mapper in a very specific format. So then that mapper knew spatially where the data it was reading from was at.
Thank you.
Just out of curiosity, your raw data, so was that coming from Monsanto generated sensor systems only?
Right now, the soil and elevation data sets are coming from public data sources.
Okay, so that's the elevation. With regard to actual sensor data that needs to be synchronized with that,
Mm-hmm.
do you have only your own proprietary system that you can bring that data with, or have you dealt with the problem of dealing with multiple different sensor systems?
So,
and of
yeah.
course, registration.
We're dealing with the problem of receiving sensor data from multiple sources. Some sources we control, as well as some sources from people that we partner with.
Okay, and have you looked into things like correlating with weather forecasts and other similar registrations?
The weather data set is, you looked at that kind of broader platform as far as using weather data to make informed decision. That's one of them on the roadmap to deal with the current product that we have. Doesn't necessarily use weather data.
Okay, just wanted to curious about the outlines of the problem.
You said you work with Cloudera and you partnered with them and developed all these solutions. Do you have any of this which is open sourced and made available to the open source community for spatial analysis or something, like processing raster files?
At this moment, it is not open source. That is something that we have possibly talked about. It is something that we have talked about.
Sure, yeah. Not something specific to Monsanto, but in general, the spatial analysis kind of libraries or something.
Mm-hmm. So we do, when you're talking about the actual polygon-to-polygon transformations and calculations, we do use a third-party tool that is open source that we're looking at, that I'm hoping to be able to make some improvements upon that. So that aren't specifically to our gridded format or any of our file formats.
Thanks.
All right, thanks.
Thanks, everybody.
Yep.